Good evening. Mechanical Engineering 3A03, week 12. Today's a Tuesday. The agenda that I'm going to do today is 2D and 3D Mohr circle. Exam, it will be held on August the 3rd, which is a Thursday, 7 p.m. to 9:30 p.m. 3 questions will be similar from homework 7, 8, 9, and 10. And the location, once I book the room, I'll let you know. Okay, so today I'm gonna start with 2D Mohr circle first. Okay, I'm gonna start. So I'm doing in such a way that I'm gonna assume that you know nothing about Mohr circle. Okay, so we're gonna look at 2D Mohr circle first. So before we do 2D Mohr circle, let's get some terminology correct first. Okay, so the first thing I'm going to like to teach is what we known as plane stress condition. As you all know, 2D Mohr circle the plane stress condition can be applied in 2D or in 3D. Okay, so I'm going to draw an element first. Okay, a 3D element first. So this is our X, Y, and this is our Z. Okay, so I'm going to draw an element okay, so this is our element. And an element usually have one surface that is bigger, or a surface plane is bigger. So over here, this surface over here is known as our XY plane. And we call it XY plane. And usually this is what we call in plane. Okay. And then this surface over here is what we call our YZ plane. And this is the way I drew the element. This is known as out of plane. And then the third surface over here, this is our XZ plane. XZ plane. And this is also out of plane. Now we can have normal stress acting on each face. Okay, but before I go on, in plane is defined by the side of the element which have or which has the largest surface area. Okay, so the XY plane has the largest surface area, as you can see. That is our in plane. Okay, that surface is our in plane. Okay, So now each surface will have a stress, a normal stress, which I'm going to draw now. So this is stress X, right? Because it's moving in the X direction. Over here, this is stress Y, moving in the Y direction. And then we have one more over here, which is our stress Z, going in Z direction. So if we look at a plane stress condition, if we were to look at plane stress condition, so condition number one, okay, when it's plane stress is when stress X and stress Y is not equal to 0. However, stress Z is equal to 0. When this is the case, we call it plane stress condition. Okay. Condition number two, there can be plane stress where stress X and stress Z is not equal to 0, where stress Y is equal to 0. Okay. And that's condition number two. And then the third condition is where we have stress Y and stress Z is not equal to 0, where stress X is equal to 0. Okay. So if any one of these condition is met, it's what we call a plane stress condition. Okay, so we will not use so much of it over here, but when you take finite element in your later years in your degree, you will see plane stress condition. So you have to know what does it mean. Okay. More important, the in plane. Okay, more important is this statement I make. The in plane is defined by the side of the element which has the largest what? Surface area. Okay, so the one that has the largest surface. So this case, this has the largest surface area. As you can see, that I'm highlighting in yellow now. Right, it's the XY plane. So the XY plane is known as in plane. Now, do not have the misconception that the in plane is always going to be the region where it fails. Not necessarily true. Okay, so don't have that misconception. It's just the way we address it. XY plane with the largest surface is our in plane. YZ is our out of plane, and XZ is our plane for this case. Just purely because of the surface area that we draw is smaller. Okay, right. So let's do one example on Mohr circle, and while doing this example, we can see we can look at a lot of definition. Okay, so I'm going to go through an example. Okay, so for this example, we have a transformation. Again, this is going to be 2D first. This will be your X, and this will be your Y, and then we will draw our element. We will draw our element. Okay. So this area is the biggest area that we have drawn. So is our in plane is our XY plane. Okay. Right. Then for this case, we will have stresses in the X direction. And this is going at 40 megapascal. And then we have the other direction coming down. Is going at minus 80 megapascal. Okay. And then we have, but usually what you see, they won't write minus. Okay. They will usually just write down 80 megapascal. Okay, but when you see how the arrow is pointed, you know it's in compression. Then you have shear, right? So shear So this is our shear. So our shear is 20 megapascal. Okay. So a few things that you can see over here, right? When the forces or when the stress are acting normal to the surface, right? These are all normal to the surface. I'll use a different color, pardon me. When it's normal to the surfaces, right? We call them as normal stress. So for this case, this is our stress X, right? And this is our stress Y, right? So when it's pointing away, we call it tensile, and we tend to call it positive. When it's pointing towards, we call it compressive. So it's usually negative, right? Then we have our user shear over here, and we know that this is our shear XY. It's equal to shear YX, okay? So this is known as positive shear. I'll write down here, okay? So this is known as positive shear. Now in shear, whether is it positive or negative, they are either as good or they're either as bad. It's not like in normal stress, right? Sometimes tensile stress is no good for brittle material, okay? Sometimes compressive stress, or usually compressive stress, the yield strength is higher, okay? In shear, positive or negative shear is as good or as bad. You cannot say that, oh, this material can withstand higher positive shear or lower positive shear. It does not apply to those rules. So why do we call that positive shear? Okay, so I'm going to draw two elements. One element over here. Bear with me. I'm going to shut down my bed. It's because my screen is very slow. Okay, hopefully now it works better. So I'm going to draw two elements. Yes, you can see over here. And in these elements, I like to draw a transformation or original zero. Okay, so this is our Y, and this is our X. Likewise, this is our Y. This is our X. Okay, so in shear, there's only two configurations. Okay, so one configuration looks like this. And the other configuration looks like this. So the one on the left hand side is what we term positive shear, and I'll explain to you why. And the one on the right is what we term negative shear. Okay. So why is it? If you look on the surfaces, if you look at the surfaces now, this surface over here, right? If the center is 0, 0, right? This surface over here, right? So I'll call area X is positive, right? Over here, area Y is also positive. Okay. And then if you go down here, area Y is negative, right? Relative to this origin over here. And this over here, area X is negative, right? Now, if we were to now focus on the shear force, right? If we now focus on, so this shear force or shear stress, right? So this is shear intersecting plane is X, going up in the Y direction. It is positive. Okay, why is it positive? Because it's going up. And over here, it's also positive because it's going from left to right, right? So positive times positive give positive, right? So if you look at, I'm going to highlight in green, right? Positive multiplied by positive, you get positive, right? Positive over here multiplied by positive. Area is negative, the shear stress is negative, positive. Negative minus multiplied by negative is positive. So this is why we call positive shear. And then in terms of positive shear, I'm going to sketch the deformation pattern. This is how the deformation pattern will look like for positive shear. Okay, so I'm drawing orange. That is how the deformation pattern will look like. Okay, so this is how the deformation pattern will look like. So this is the deformation pattern for positive. Now, how do we get the deformation pattern? Right, is if you look at this stresses over here, and then if you pinch the corner, if you pinch this corner, I'm highlighting in red now, right? It's stretched in that direction. Okay, so this is the deformation pattern for positive shear. And then in terms of negative shear, we know that this is also shear X intersecting the plane X, shear stress in one direction, shear YX, right? So what you can see over here now, if we were to draw the deformation